Hey, have you ever been chatting with an AI, asked it something, and gotten this super confident, like definitive answer that just turned out to be, well, totally wrong?
Oh, yeah. Happens all the time.
Like it absolutely knew that some famous event happened on a Tuesday, but, history books clearly say Wednesday.
Exactly. Or that your favorite author was born in one city when, nope, actually another.
That's the fascinating puzzle we're tackling today, AI hallucinations.
Exactly. What we're seeing in our materials is that an AI hallucination happens when these neural networks produce outputs that sound completely plausible.
Right, they make perfect sense grammatically.
But when you check the facts, they're just plain wrong or maybe completely made up.
Like a language model stating with total certainty that a peace treaty was signed in, I don't know, 1955.
Yeah, when historical records firmly place it in 1958, that kind of thing.
Right. And the really kind of mind-bending part is this isn't just a human hitting the wrong key. The AI isn't making a random typo.
No, not at all. What we've looked at tells us that these hallucinations come from the patterns the model has learned during its training.
So it's generating what feels like the most statistically likely answer based on like the massive amounts of text it's seen.
Precisely. Without actually having any real-world understanding, of whether that information is accurate.
So the key insight for you, the listener, is that the AI is guessing the most likely next word. It's not recalling a definite fact from memory.
That's a really crucial point. And these kinds of confident errors are especially common in what are called generative
Okay,
models.
generative models.
Yeah, these are the AI systems specifically designed to create new content based on the data they've been trained on, rather than just, say, analyzing or categorizing stuff that already exists.
So we're talking about AIs that aren't just looking at what's already out there, but are actively, producing something new.
Right, and beyond the language models we hear about most, like the ones using transformer technology that power things like ChatGPT, the underlying issue of venerating plausible but incorrect information also exists in other AI systems designed to create data, things like VAEs or JANs, though they work a bit differently.
Okay, interesting.
And as our sources highlight, these hallucinations aren't some rare glitch. They happen surprisingly often, actually.
And for a whole bunch of different reasons, it sounds like.
Yeah, it can come down to the fundamental way these models are built, their architecture, or even just statistical quirks, really, in the generation process itself.
What really stands out, though, is just how sure these models sound when they're delivering these incorrect answers.
Absolutely. There's no hesitation, no maybe.
They just confidently state things that are simply, well, false.
Uh-huh.
So for you, our listener, the core question we're digging into in this deep dive is, why does this happen? What's going on behind the scenes that leads these seemingly intelligent systems to confidently kind of invent information?
Okay, well, let's start by looking at the fundamental way these generative models are designed. As our materials explain, models like GPT aren't storing and retrieving facts like a database does.
Right, not like looking something up in an index.
Exactly. Instead, they're modeling probabilities. When you give them an input, they're essentially calculating how likely different words or pieces of text are to follow that input based on everything they've learned.
Okay, let's really unpack this probability idea a bit more. So when you ask one of these transformer models a question, it's not searching for a pre-written answer somewhere.
Yep.
Instead, it's trying to figure out, based on all the text it has processed, what the most probable next word should be.
Uh-huh. And then the word after that, and so on, building the answer piece by piece.
Okay.
Precisely. Think about you asking, what is the capital of France? The model takes that question, breaks it down into smaller chunks called tokens,
Tokens, right.
and then uses mathematical representations of those tokens. It feeds these into its internal architecture, the transformer body, does some calculations, and ultimately spits out a probability score for every possible next token in its vocabulary.
Wow, okay. Every single one.
Well, practically speaking. The source material illustrates this, well, it's calculating the conditional probability of Paris appearing next, given the question, what is the capital of France?
So because it's been trained on just a massive amount of text where Paris very, very often follows the capital of France's, the model assigns a really high probability to Paris being the correct next word.
Exactly. But, and here's the key thing our sources point out, less obvious answers, even incorrect ones like London, might still have a small but importantly not zero, probability.
Why would it give London any probability at all?
Well, it could be because the model has seen those words, capital and London, used in similar sentence structures, maybe talking about the capital of the UK, or even in completely unrelated contexts that just happen to share some structural similarity.
Ah, okay. So it sees a pattern, even if the context is wrong.
Right. And here's where it gets really interesting for hallucinations. If the model, maybe just by chance during the generation process, happens to select a token that has a low probability, say, London, with only a tiny 1% chance,
Uh-huh.
that becomes a hallucination. Even though it's statistically really unlikely given the input capital of France, it can still happen.
And the way transformers are designed, this whole next word prediction thing, that makes them particularly vulnerable to this, doesn't it?
Absolutely, because they're building the output step by step, word by word.
So if it makes a mistake early on.
Exactly. If the model makes a wrong prediction early on in the sequence, like picking London instead of Paris, that initial error can have a cascading effect.
How so?
Well, that wrong word, London, influences the probabilities it calculates for all the subsequent words. It might then start generating text related to London, potentially leading the model further and further down a completely fabricated path.
Wow. So one small probabilistic error can snowball.
It can. Plus, because its core function is simply to predict the next word, it'll often keep generating, even if it doesn't really have enough solid information to go on for your specific query.
So it falls back on related but maybe ultimately incorrect patterns it picked up elsewhere.
Precisely. It's filling the gap, but sometimes with the wrong material.
Okay, so the fundamental design, the next word prediction, plays a huge role. But our sources also bring up that the method we use to actually choose which word to output from those probability scores the decoding strategy that also contributes.
That's right. There isn't just one way to pick the next token once you have all those probabilities.
Okay.
So one straightforward method is called greedy decoding. It's pretty simple.
Mm-hmm.
At each step, you just pick the token with the absolute highest probability score.
That sounds safe.
It's generally safer, yes.
Okay.
Less likely to go totally off the rails. But it can sometimes lead to outputs that are a bit, well, repetitive or maybe lack creativity. Very predictable.
Okay.
Then there's just sort of randomly sampling from the entire range of probabilities. Every token has some chance of being selected, weighted by its likelihood score.
Ooh, that sounds like it would lead to more creative, maybe unexpected outputs.
It can, definitely,
Mm-hmm.
but also a much, much higher risk of generating complete nonsense or, hallucinations. Bit too chaotic.
Right, okay.
Yeah.
So what's actually used most often?
Well, that's why the most commonly used methods are things like top K and top sampling. They try to find a middle ground, basically.
Top and top pay, how do they work?
So with top K, you only consider, say, the top K most probable tokens, maybe the top 10 or top 50, and then you randomly sample from just that smaller group.
Okay, narrows it down a bit. And top.
Top P, which is also known as nucleus sampling, is slightly different. You look at the list of tokens ranked by probability, and you keep adding them to your potential selection pool until their cumulative probability reaches a certain threshold, let's say 70% or 0.7, which is P.
Ah, okay.
Then you randomly sample only from that set of tokens that make up the top 70% probability mass.
Gotcha. So with top, even if you're focusing on the most likely options that together make up, say, that 70% chunk, there's still a chance that a less probable token, one that's still within that top bracket but maybe incorrect, gets picked.
Exactly. It might be the fifth most likely word, still part of that 70%, but actually wrong in context. That can lead to a hallucination.
So top K is like saying, we'll only consider the 10 most likely words, maybe safer, but potentially repetitive.
Right.
And top A is more like, we'll consider enough likely words until we're pretty sure we've got the right idea, allowing more variety but still carrying that risk.
You've got it. The specific values chosen for K or P are really important adjustments engineers make to balance that trade-off between coherence and creativity, or you could say between the risk of hallucinations and the desire for more diverse output.
Makes sense. Now, another really significant piece of this puzzle, it seems, is the training data itself. What we've read really emphasizes that while these data sets are absolutely enormous, just mind-bogglingly huge,
Billions, sometimes trillions of words.
they're still finite. Right. They can't possibly contain every single fact or piece of context that exists in the world.
That's a fundamental limitation, yeah.
Yeah.
If a model is asked a question about a very niche or obscure historical event, maybe something that wasn't well represented in the data it was trained on,
Uh-huh.
it might try to kind of piece together an answer based on patterns it has seen in related but ultimately different areas or
So
topics.
it's essentially inventing details to try and fill in the gaps in its knowledge.
You could put it that way, yeah.
Yeah.
It's generating what seems plausible based on related patterns.
And a massive portion of this training data comes from, well, the internet.
Yep, the web.
Which, I mean, while being this incredible wealth of information that's pretty easily accessible and relatively low cost to gather.
Huge advantages.
It's also described in the sources as noisy, which makes perfect sense when you think about it, right?
Absolutely.
Mhm.
The internet is just full of factual errors, contradictions, opinions stated as facts, biases, and even completely made-up stories or fiction.
So the AI is learning from all of that.
It can be, yes.
Yeah.
And the automated methods often used to collect this data, things like web scraping, aren't always very good at filtering out the unreliable or, false stuff.
So if a model like GPT happens to scrape, I don't know, a satirical article or maybe just a forum post where someone jokingly claims London is the capital of France,
Right, like in our earlier example.
the model might, as our sources suggest, actually assign some small degree of probability to that statement being true.
It could, yeah, because it saw that sequence of words together. It doesn't inherently know it's satire or a joke. When you multiply that possibility across billions and billions of training examples,
Uh-huh.
these little bits of misinformation, these errors, these biases can unfortunately become subtly embedded within the model's learned patterns.
Wow. So the crucial insight for you, the listener, is that the very information these powerful AIs learn from can itself be flawed or biased or just plain wrong, leading to these confidently wrong outputs later.
Exactly. It learns what is shown, warts and all.
And it's not just about outright factual errors in the data, is it? Our materials also point out the issues of bias and ambiguity that are just inherent in the human language and therefore in the data.
That's a huge factor, too. The data reflects the complexities, the perspectives, sometimes the prejudices of the world it came from.
And that can lead models to incorrectly favor certain viewpoints or make assumptions that aren't universally valid.
Absolutely. And AI learning from that data can unfortunately inherit and sometimes even amplify those same imperfections.
Okay. So we've looked at how the models are designed, the decoding strategies, the limitations and flaws within the training data. The last major area that seems to contribute to hallucinations is this idea of um, generalization and reasoning, or maybe more accurately, the current lack of true reasoning in these AI models.
Precisely. Neural networks, especially these massive transformer models with their billions, sometimes trillions of parameters,
It's hard to even imagine.
it really is.
Yeah.
They are essentially compressing all that data they've been trained on into this vast network of interconnected weights and biases. They simply don't have the capacity to explicitly store every single fact they've ever encountered like a perfect library.
So they have to generalize.
Exactly. They identify and generalize patterns so they can perform well on a wide variety of tasks, even ones they haven't seen the exact examples of before. That's their strength, in a way.
But that process of generalization can sometimes lead to errors, right? Like in that classic example we saw, the model learns birds can fly because most examples of birds involve flying.
Uh-huh.
But it doesn't inherently understand that penguins, while definitely being birds, are a key exception to that rule. It hasn't learned the exception well enough.
That's a perfect illustration of overgeneralization. It happens when the specific input, like asking about a penguin, doesn't quite align with the dominant pattern the model has learned so strongly.
And it's really important to remember, as you said, these models don't reason like humans do.
Not even close, really. They're predicting the most likely next token, based purely on statistical probabilities derived from the patterns in their training data. They don't possess a logical, real-world understanding of cause and effect, or truth versus falsehood, or the relationships between concepts in the way we do.
That point about arithmetic in our sources was really illuminating. When we ask an AI, what is 2 plus 3, it's not actually performing the mathematical calculation.
Generally, no. Especially for simple stuff it's seen countless times.
It's predicting 5 because it has just encountered that specific sequence of tokens, 2 plus 3 plus 3, 5 together, so many times in its training data.
Exactly. It's pattern recognition. It's learned that 5 is overwhelmingly the most probable token to follow 2 plus 3 of it.
So if the surrounding context in the input prompt was somehow noisy or misleading, maybe mentioning other numbers, it could statistically predict a wrong answer, like 6, just because some pattern involving those other numbers slightly skewed the probabilities.
It's possible, yes, because it's not calculating. It's predicting based on learned associations. That's mind-blowing, isn't it?
It really is. So even something that seems so fundamental to us, like basic math, is often just sophisticated pattern matching for these models.
That's a key insight, definitely.
Mm.
And fundamentally, tying this all together, these models lack what's often described as a world model.
A world model.
Yeah, or any sort of robust internal mechanism for fact verification.
Mm.
They can't easily cross-reference their potential outputs against a broader understanding of reality to check if they logically make sense or are consistent with known facts outside of the patterns they learn from text.
They can't step back and ask, wait, does that actually make sense?
Not in the way a human can, no.
Okay, so now we have a much clearer picture, I think, of why these hallucinations happen. It's a mix of the design, the data, the way they think. So what can actually be done about it? Our sources touch on several strategies for, reducing these inaccuracies.
Yeah, thankfully people are working hard on this. One crucial area is focusing on improving the training data itself.
Better data in, better results out.
Essentially, curating high-quality, diverse, well-cleaned data sets is really essential. Now, it can be more expensive and definitely more time-consuming than just scraping the web,
Sure.
but cleaner and more comprehensive data helps significantly in minimizing that noise and filling in some of the information gaps we've been discussing.
Right. What else?
Another important approach is fine-tuning the models. After the initial massive pre-training, you can fine-tune them on more specific, high-quality data sets relevant to particular tasks.
And often using techniques like reinforcement learning from human feedback, RLHF.
Exactly. RLHF is a big one. Humans review the model's outputs, rate them, provide corrections, and that feedback is used to further train the model, basically reinforcing correct patterns and penalizing it for generating fabricated or harmful information.
Okay, training it to be better behaved, essentially.
Kind of, yeah. Then there's retrieval augmented generation, or AI, which is another really promising technique that's been gaining a lot of traction lately.
ROI, how does that work?
The core idea here is pretty neat. You pair the language model with an external, reliable knowledge source. Think like a curated database or a collection of verified documents.
Okay.
So when the model needs to generate a response, especially one that requires factual information, it first retrieves relevant information from this trusted database.
It looks things up first.
Kind of. And then it uses that retrieved, verified information to augment its own generation process, grounding its answer in actual verifiable knowledge rather than just relying on its internal learned patterns.
That makes a lot of sense, essentially giving the AI a reliable source to check its potential answers against before it speaks.
It's a powerful approach for fact-based queries.
And our sources also mention a perhaps less glamorous, but still really important strategy, training models to express uncertainty.
Yes, this is surprisingly important. Teaching the model to actually say, I'm not sure, or I don't have enough information to answer that accurately.
Instead of just confidently making something up.
Exactly. Especially when the probabilities it calculates for different potential answers are very close, or when the input prompt itself is ambiguous. It helps manage user expectations and avoids that confident presentation of information that might very well be incorrect.
Just being honest about its limitations.
Basically, yes.
So just to recap for everyone listening, we've seen that AI hallucinations aren't just random glitches or mistakes.
Not at all.
They arise from the very way these generative models are designed, focusing on predicting probabilities, finding patterns, rather than having a true grasp of facts or truth.
Uh-huh. And the specific decoding strategies we use to select the outputs matter too.
Right, and the inherent limitations, the noise, the biases within their massive training data sets play a huge role.
And finally, that current absence of genuine human-like reasoning and built-in fact-checking capabilities, all these things contribute.
It's a complex mix of factors.
It really is. But, importantly, while these are significant challenges, the various mitigation strategies we've discussed.
Better data, fine-tuning, RAG, teaching uncertainty.
Exactly. Things like improving training data quality, using RLHF for fine-tuning, leveraging retrieval-augmented generation, and training models to express uncertainty, they all offer a promising path forward.
Towards building more reliable, hopefully more trustworthy AI systems.
That's the goal.
So as we wrap up this deep dive, here's maybe a really thought-provoking question for you listening to consider. Given that these AI models are fundamentally designed to identify and learn from patterns in data, what does the very phenomenon of hallucination really tell us about the nature of knowledge, maybe even truth itself, when it's acquired solely from that kind of statistical pattern matching on data?
That's deep.
Yeah, and maybe in a world that's becoming more and more reliant on information generated by AI, what are the potential implications, the risks, when these systems confidently present answers that are, at their core, simply sophisticated guesses or patterns that might be completely detached from reality?
Something to definitely keep thinking about.
Absolutely. It's a fascinating and, frankly, absolutely crucial question to keep in mind as this technology continues to evolve.